Hello. Good morning.
Good morning, sir.
Adarsh. Yeah. Adarsh. Shashi Kumar. Your mic. Yeah.
Good morning, sir.
Good morning. Good morning. Okay, let's start our class. Okay. So, what we studied in the last class? Just tell me. You can see the OneNote, right?
We transfer through spherical walls and
Steady conduction, right?
cylindrical
Steady
walls.
conduction through planar wall, cylindrical wall, and come on, spherical wall. Yeah. Then we also obtain the log mean area and geometric mean area. Okay. So what is the log mean area actually? What is log mean area? Yeah, Adarsh, you can tell me.
So
Log mean,
cylindrical wall and planar wall when it is like equivalent, same thickness,
You have to
same
tell
material.
equivalent area of planar wall, okay, which will have same heat transfer.
Same thickness, same material and temperature.
And same material. Okay. Yeah. So that is the equivalent area of planar wall. Okay, which have same heat transfer as the cylindrical wall. Similarly, we have geometric mean area, which is equivalent area of planar wall, which is having same heat transfer rate as spherical wall.
Spherical.
Yeah, and the quantities which are kept same has to be mentioned. Okay, under that conditions. Okay, so then today we will take up the composite walls. Okay, and critical thickness of insulation. So I'll cover most of the theory today's class. So from next class onwards, we will start problems. Okay. Now, we have already studied, we know what is the rate of heat transfer through a planar wall. Okay. So extension of that, like if you have a multiple layered wall, okay, then how is to be calculated through the entire wall. Okay, that is what we will see today. So you can give some example where we'll have this multi-layered walls, and what is the purpose?
Heat exchangers.
Heat exchangers, definitely not. Okay, multi-layers will not go come in heat exchangers. Okay, because there the wall should have minimum resistance to the heat transfer in a heat exchangers. Okay, I mean the heat exchanging wall between that separates two fluids in a heat exchanger should have minimum resistance. Okay, but if we want to reduce the heat transfer, okay, we have to provide the insulation. For example, if you consider the double 5 heat exchanger, then outer wall maybe can be insulated with multiple layers. Okay, but there are so many other applications, okay, where we don't want the heat losses. So then we will use this multi-layered insulation. The main purpose, what may be the main purpose of going for multi-layer? You can use single layer of insulation with the very low thermal conductivity, right? That justifies the, I mean, why you need to go for multi-layer. Resistance is there. Yeah, I am telling you this. If you have a very low thermal conductivity material, out of this, you can see the image, right? K1, K2, K3. Okay, you may be having a material which is having very low thermal conductivity, and that material itself will act as a best insulator, right? It will reduce the heat transfer very much. But why we have to go for multi-layers?
If you want to achieve different rates of
heat, okay, that is not the but But the economic point of view, if you consider the insulator which is having very low thermal conductivity may be costly. Okay, so then we have to see that to make it economic, we have to go for multi-layered insulation. Okay, so that is the main reason actually. Okay, it's not that we cannot use single layer. Okay. Okay, again, you can see the image now. You have I have shown you 3 walls of thermal conductivity K1, K2, K3. Okay, and the image shows that the temperature drop across the first wall is T1 minus T2. Temperature drop across the second wall is T2 minus T3, and temperature drop across the third wall is T3 minus T4. Okay, so here one more very important point is there, and that is I have shown the temperature variation in a continuous way. There is a slope difference. The first wall, the slope is more compared to the second one. Okay, and third one, the slope is the largest one, right? Now, my question is, okay, first thing is I will explain you this continuity. This is ideal situation. The continuity in temperature, or that you can see that the temperature at the end of the first wall, that is T2, and that point where the second wall begins, that the temperature is also T2. But this is a perfect thermal contact assumption. Perfect thermal contact assumption. To understand what is perfect thermal contact. Okay. What does that means? We have every molecule or the atom of the first wall is touched with the neighboring wall's atom. Oh, okay. That is highly impossible. You know, you have studied material science. Okay, how the surface is there, surface roughness, everything you know now already. So when you come bring 2 walls close together, okay, there is some gap between these 2 walls. Okay, that is in micro level, atomic level, you can say, or the nano level. There is some gap, so you cannot get that perfect contact between the atoms or molecules of 2 walls. Okay, so that is the problem. There is a problem, and that is because of that we have extra resistance when we bring 2 walls close to each other. Okay, for time being we ignore that the contact resistance, and we take up this continuity in temperature. Okay, so the perfect contact thermal contact assumption is made here. And the other point is very important to understand is, by looking at this temperature drop, you should be able to tell me which material has a very low thermal conductivity and which has very high thermal conductivity. Okay, you have to, by looking at this temperature drop, you have to come to know that the highest thermal or the resistance to the temperature heat flow is offered by which wall and all that. Okay, tell me which one is highest thermal conductivity in this K1, K2, K3. If you have to write the first value, largest value first, then which one should I write?
K3. K3.
K3 is the largest thermal conductivity. Anybody opposed to that?
K2, sir.
Yeah, tell me.
K2, sir. K2.
K2.
K2 is the highest thermal conductivity in the. Okay. So what is the reason?
The temperature change.
Yes, minimum. Okay, that means the wall is allowing
K
more
is
heat transfer.
inversely proportional to temperature change.
Yes, yes. Okay. So you have to get when the thermal conductivity is very low, the temperature gradient will increase. Okay, temperature gradient will increase. So K2 is the largest one. Then next, compare K1 and K3.
K1.
K1. Okay, then K3. So this is just by observing this temperature drop. Okay, you could make out. So under steady state, we know that the rate of heat transfer through all these walls should be same, and this is just steady state heat transfer we are considering. So if this is the temperature drop profile, then we can easily write this. Okay, K2 is greater than K1 is greater than K3. Okay, now let's write the heat transfer through the first wall, or you can write at steady state. Heat transfer through first wall is same as, okay, second wall equal to, or all the wall, it should be same, or you can write Q1 equal to Q2 equal to Q3 equal to. So what is the heat transfer to through the first wall? Q1, you know the temperature difference, you know thermal conductivity, assume that area is A, then we can write this is Ka T1 minus T2 divided by X2 minus X1. Okay, here I have given L1, L2, L3, so you can simply write that X2 minus X1 is nothing but L1. Okay. So similarly, you can write for the second wall, third wall. Okay. Or you can write this one as T1 minus T2, that is the temperature drop across the wall divided by thermal resistance, which is L1 divided by Ka. Okay, so I'll write this as T1 minus T2 divided by RK1. Okay, so it's RK1. I'm using K because it's conduction resistance. Today we will take up the other L1 by Ke. Okay, so we can similarly write Q2, Q3. Q2 will be equal to, okay, T2 minus T1 divided by thickness of the wall L2 divided by K2. This is K1 here. K2 A.
T2 minus
Yeah.
T3. T3.
T2 minus T3. Sorry, T2 minus T3. And this is, you can write same way, T2 minus T3 divided by RK2. And similarly, you can write Q3 equal to T3 minus T4. Something is wrong with the. So can you see that something is getting erased? Yeah, tell me, you can see everything or something is removed here?
Something is removed.
So
T2
it's
minus
removed,
T3 is removed, sir.
It's removed.
Yeah. I don't know what this bug is. Huh? Okay. So you already wrote that, right? I will not write again. So Q3 equal to L3 divided by K3A, and that is nothing but T3 minus T4 divided by the conduction resistance of the wall 3. Okay, so we can now write, so since we know that Q1 equal to Q2 equal to Q3, okay, we can write Q into, oh, yes, the temperature difference T1 minus T2 can be written as Q1 into RK1, okay, or Q into RK1 if you don't want to write. So because similarly, temperature difference T2 minus T3 is nothing but Q into RK2, and T3 minus T4 equal to Q into RK3. So you can add these 3, 1, 2, and 3. So what do you get? You add T1 minus T2 plus T2 minus T3 plus T3 minus T4. Okay, left hand side. And on the right hand side, Q is common. So you have RK1 plus RK2 plus RK. So simply we can see from the left hand side minus T2 plus T2 minus T3 plus T3. So the overall temperature difference is enough for us to calculate the heat transfer rate. But the resistance has to be added up. RK1 plus RK2 plus RK. Simply, you can write now Q is nothing but temperature drop across the wall, all the walls, that is T1 minus T4 divided by total resistance of the 3 walls, RK1, RK2 plus RK. So that is why we use the electrical analogy here. It's very easy. Okay. So we here itself, I think it is shown here. So temperature on this wall, this side of the wall is T1, and temperature at the end of the third wall is T4. That is enough for us to calculate the rate of heat transfer. So, okay, this is T1, and there are 3 resistances, and here the temperature is T4. So RK1. Okay, so this is very easily you can remember. Only you have to write the electrical circuit and you should know the formula for the resistance. That's all. Thermal resistance of planar wall, or conduction resistance of planar wall, cylindrical wall, and spherical wall. You can easily do the problems. So to increase the complexity of the problem, we can design different ways these walls. Okay, the wall can be combination of multiple walls. Okay, with having different areas, not same area but different areas. So for example, if I show you, so let's say I have a first wall, then the second wall, so I think we have limited colors. The third wall, same thickness as the second wall. Okay, and there's one more wall. Okay. Okay, this is the having thermal conductivity K1, this is having K2, this is K3, and this is K. But the area of this wall is, say, A1, and this is also having same area, A. This side, this wall is our same area, but this is, say, having the 50% of that area A, or 0.5 A, and this is also having 0.5 A. Okay, So this problem, how you'll solve it? You have to again write the electrical circuit. Very easily you can do that. Okay. The temperature here will be T1 and temperature on this wall entirely T2. Here it is T3 and this is T4. So you can draw the electrical circuit. This is the resistance of first wall RK1. Then there are resistance in parallel, not in series. Okay, resistance in parallel.
Sir, wouldn't there be two temperatures for K2 and K3, the right wall?
Yeah, I'll tell you. I'll come to that point. Okay. This is R4, RK4. What about this one? RK2, and this is RK3. So temperature here is T1. Temperature here is T. So your question is the temperature entire surface here is. I'm telling it's T2, and here it is T3. So what was the doubt? Yeah. Rajat, right? Who asked?
So that because
No, Nachikeet.
K2
Okay.
and K3 represent, yeah. So because K2 and K3 represent different materials, shouldn't
Different
there be
material.
different
Exactly.
temperatures
Yes.
on
Yes.
the right side of them?
Yeah. So you're in right. I mean that doubt should come to everyone's mind. Okay. That means you're listening. Okay. So actually, we have to see this one. Okay. If one material having very large thermal conductivity, different thermal conductivity here. Okay. So the one which having the low thermal conductivity will allow more heat transfer through that. Okay. But ultimately at the steady state you have same temperature. Okay. You cannot have. This is the law of nature. You can see even in electrical circuit, right? So what is the potential value at the junction here? You cannot have different potential at that junctions. Okay. So it's very natural that if K2 is less than K2 is sorry. So I have the same problem again with the one note.
I had one doubt.
Yeah. Okay. 1 minute. I'll come to that. Okay. Yeah.
So isn't steady state achieved by changing the area or length, or is it like just achieved?
No. Steady state is not achieved by changing anything, area or. If you change something, then it will not reach steady state. Okay. Steady state in heat transfer problem is because you are giving same heat input and removing same heat out. Understand? There is a constant flow of heat. Constant rate of heat input on the left side. For example, if you are taking the heat transfer in the positive x direction, then Q heat supplied to this left wall and the heat removed from this wall is same. It's maintained same. Okay. So this is very
So your screen is not
common
visible.
problem. Yeah. Yes.
Sir, the screen is not visible.
Oh, sorry. I have to share it again. Yes. Yeah.
So,
Yeah. I'll share it. Okay.
no, sir, I have a doubt.
Okay. 1 minute. Yeah. Tell me.
Sir, in steady state, the time change of temperature difference is 0, right? The temperature difference remains constant over time.
In steady state, temperature difference remains constant over time. Correct.
Yeah. So let's say I have a bottle of water that's heated up and I've kept it outside. So exposed to ambient temperatures. Now let's say the bottle is at 90 degrees Celsius. Water is at 90 degrees. Air is at 20 degrees.
Yes, exactly.
And I'm constantly supplying heat to the water and keeping it at 90 degrees. So
okay. If you're keeping that water at 90 degrees without changing its temperature, okay, yes, then it is a steady state problem.
Now, sir, instead of keeping it outside in the air, I'm keeping that bottle in a chamber, of which the temperature I can control. So let's say
you can control the temperature of the room. That is important. Okay. Then again it will be steady state problem. You can say.
So let's say the initial temperature difference was 70 degrees, 90, 20. If the temperature of the water drops to, let's say, 88.
No, you're telling you're changing from your point. You told me that you will keep the temperature at 90 degree initially.
So that is
then why you're now changing?
No, that is one condition in which the temperature difference is constant. 90 degrees and 20 degrees. Now the other condition is where I am changing the temperature of the water, right? From 90 to 88, let's say I am also changing the temperature of the surroundings. I'm bringing that to 18. So 70 degrees is still remaining. Is that also steady state?
No, we don't. Okay. If you are changing from 90 to 88, okay, and 20 to 18, then there is a transience. Okay, it will not suddenly change. But once you maintain that, once you maintain 88 and 18 for sufficient time, then again it is a steady state.
But if they simultaneously change and the temperature difference still remains constant, then also it's not steady?
No. Simultaneously, whatever it is, okay, you cannot change it inside the wall of the your bottle. You can change, and that is a very idealistic. How can you change the 2 degree temperature in one short moment? Okay, it's not possible, but that is not practical. Again, if you could do it, then inside the wall of your bottle, the temperature is in transient. Okay, the earlier profile was different. Now the profile has to adjust, temperature profile has to adjust to the new temperature conditions. So there is a transient, okay, for some time. Again, if you are maintaining at 88 and 18, then again it will reach steady state, and you can analyze it as steady state problem. Okay, understand that clearly. So you cannot simply suddenly make one steady state to another steady state in one sudden instant. Okay, so it involves a transient phase. Got it right?
So you're saying the moment I change the temperatures, even to bring it to a constant temperature difference, there will be transients.
Yes, exactly. Okay, yeah. So this type of problems.
Sir, I have a doubt.
Okay,
Sir, the heat transfer across 2 and 3, will it be equal to the heat transfer across like wall 1?
Okay,
or will
this
it be
is
half
1.
Of that?
1, this is 2, this is 3. You are telling
so the heat transfer
okay, heat transfer Q1. Okay, this is Q2, and this is Q3, and this is again Q. So Q1 equal to Q2 plus Q equal to Q4.
So the 2 and 3 will be equal, is it?
No. How come? That is why K1 and K2 and K3 are equal. Then it is same. If K2 equal to K3, then only. Otherwise, it's not. Otherwise, depending on proportionality, like if K2 is more than K3, then more heat transfer will take place from which one?
2.
If K2 is greater than K3, more heat transfer will take place from
2.
K3.
K2 is more.
2.
Conduction is more in wall 2.
K2.
Okay.
Second one will be more.
Second one will be more. Okay. If other way, K3 is more than K2, then more heat transfer will take place through the third wall. Okay. Got it, right?
Yes.
So it's proportionally, it will change. Proportional, and exactly, because if you are keeping the area exactly half, then it is a very simple problem. Okay. We can easily solve this problem. And that simply the ratio will be ratio of the, what I mean, Q2 by Q3 equal to
K2 by K3.
K2 by K3. Sorry, K2 by K3.
I had a basic.
So I'm just putting this thoughts in your mind because we can design different problems on this one. Okay, so very versatile. I mean, you should imagine how the problem should be solved. Again, if I want to divide this wall K2 or K3 into 2 layers, I can do that. Understand that if I want to divide this wall by putting 2 layers, then what will happen? Our circuit has to be changed again. So I will divide this. This is different material. This is different material. Sorry, no, I think something's wrong with OneNote. So you have to change the circuit for this case. What you have to do is we have to add one more resistance on the top side there. So, okay, so let me say this is 2 and this is 5. Okay, so 2 is already there. Here I have to change and add one more resistance there.
So here heat transfer is unidirectional, right?
Yeah, same direction, no problem. That is. So one, this is RK2, and then one more resistance RK5. Okay, RK2 and RK. So again, these two are in series, but RK2 plus RK5 are in parallel. So you know how to obtain the resistance. When you are in keeping the resistance in series, you have to add them. Okay, when these are in parallel, so you can find the equivalent for this one as RK equivalent, which is the sum of RK2 plus RK5. Okay, then you find the equivalent of RK equivalent and RK3. How you do that? Or I'll write RK equivalent 2. How you do it? 1 by RK equivalent 2 equal to 1 by RK3 plus 1 by RK equivalent 1. See, this problem becomes more complex. Now, this has to be obtained first, and you have to reduce this circuit back to what is this one? RK1 is there. Then what is this one? Entirely together, you have to put as one more resistance there, and this is RK4. What is that? The middle one. What is this resistance? Is
R equivalent 2.
Yeah, RK equivalent 2. See, a simple problem just by modifying, putting one more extra layer, the problem became more complex. Okay, so understand the process. Okay, everything you can borrow the idea of your basic electrical course. Okay, where you have done this type of problems with resistances in parallel, resistances in series, and all. Okay, so refresh it. Those people who do not remember, you can go back and refresh your knowledge on this. Okay, basic circuit, resistance circuits, RC. Okay, so we will move on to the other coordinates of the type of wall, cylindrical and spherical wall. So if you understand, for planar wall, 10 is just an extension of that. So you don't have to do much there. Okay, for the composite cylindrical wall, what you have to you can write again same way. we can write the conduction resistance RK1, RK2, and RK3, and the same thing we can write here, that the rate of heat transfer through the first wall equal to second wall equal to third wall at steady state. And you can write, okay, Q equal to Q1 equal to T1 minus T2 divided by RK1. Similarly, Q2 equal to T2 minus T3 divided by RK2, and Q3 equal to T3 minus T4 divided by RK. And what is RK1, RK2, RK3? You have to tell me. This is a cylindrical wall, so immediately that formula should come to your mind. Okay. What is RK1? ln. Write it again and again, because you will be using this multiple times. Okay. So you should not confuse between the formula, resistance formula. Tell me. Isn't it? Resistance of the first wall, okay, is nothing but ln R2 by R1 divided by 2 pi LK1, cylindrical wall. Second wall, come on, tell me. ln R3 by R2 divided by 2 pi LK2. Okay. Similarly, RK3 is ln R4 R4 divided by R3, 2 pi LK3. Okay, and you can write the overall. The process is same. You can write T1 minus T2 equal to RK1 Q1, and this is nothing but Q itself. Everything is same at steady state. So you can add these three equations and write. You can finally write Q equal to T1 minus T4 divided by the resistances RK1 plus RK2 plus RK. Okay. So RK1 okay. So any problem here or anything you don't understand? The only thing is you have to substitute different formula for resistance. The process, everything will remain same. Okay. So the formula for calculating the rate of heat transfer is same as the planar wall. Okay, but only thing is to substitute the resistance formula correctly. So similarly, you can do it for the spherical wall. Okay, so you just use same formula here. Rate of heat transfer Q is nothing but same T1 minus T4. T1 is this surface temperature is here, and T4 is the outermost wall's surface temperature divided by the resistances RK1 plus RK2 plus RK. What? Okay, now tell me what is RK1?
R2 minus R1 by 4 pi R1.
Yeah, Rajat. Okay. RK1 equal to, yeah. Tell me.
R2 minus R1.
R2 minus R1, good, divided by
4 pi R1 R2.
R1 R2.
R2.
Okay. So similarly, you can write RK2, RK3. RK2 will be R3 minus R2 divided by 4, 5 K R2 R3. R4 minus R2 R3, sorry, R3 4 5 K R3 R4.
So shouldn't it be
Okay.
K1, K2, K3?
K1, K2 is missing. Oh, sorry. The material is different. So K1, K2, K3. Okay. I think now you should spell it very easy, right? So what you have to do is
Can you
go
scroll?
for electrical analogy. Okay. Use the electrical analogy and write the circuits and just remember the resistances, how to write the conduction resistances. Okay. That's all.
So can you scroll up?
Srinivas, yeah, tell me.
So please scroll up.
Off. Okay. Yeah. There. Yeah. Is it okay? Or still up?
No, enough.
Yeah.
So shouldn't it be RK3? So Q3 equal
Which
to
one? Which one?
So Q3 equal to T3 minus T4 by
4
RK3,
divided by
right?
RK3. Correct. Yeah. Yes. Thank you.
So please scroll down.
Okay. So one more thing is like that complex wall design I took after the planar wall. So that type of questions are only in case of planar wall. Okay. It will not be asked in the composite, spherical, and cylindrical wall. So don't worry. For planar wall, it's very easy. But I have shown you the process. Okay. So that process can be applied and you can solve the problems very easily.
So can you give example of spherical wall heat transfer surfaces?
Okay, I think I discussed in the last class. So most of the times we will go for the storage vessels of cryogenic fluids. Okay, so spherical storage vessels. So again, because this cryogenic fluids will be stored under high pressure. Okay, so you know that spherical uh, vessel, we don't have that stress concentration points or okay, it's a uniform proof stress in the wall. So that is why we go for that spherical storage vessels. Okay, and you know when we store a cryogenic fluid in a vessel like that, I think you heard the term cryogenic in thermodynamics at least, isn't it? No, Srinivasa.
Yes, sir.
So,
Yeah. Okay. So you know the temperatures, right? So the very low temperatures there, and the outside room temperature, there is a heat loss to the surrounding. So there will be multi-layered insulations. In addition to that, there is also radiation heat loss to be minimized. So radiation shields also will be used between the layers. So that multi-layered composite wall is much complex. Okay. But what problems we consider in the class in this course are much simple. Okay, yeah. Okay, so we move on to the next important topic, very important, and I think those people who are studying design of heat exchangers, okay, you will be needing that overall heat transfer coefficient. Okay. Okay, so we'll derive that. So other important topic is the combined conduction and convection heat transfer. Combined conduction and convection. Okay. So what is this actually? Till now we never took these two together. So I just defined the temperature of the wall on the left side and the right side, or in the between the layers. Okay, and we solve the we derive the equation. But how we can heat the wall, okay, to a temperature T1? Okay, maybe we can use some electrical heater, or generally, if you take up the heat exchanger problems or any practical problems, okay, so there is a hot fluid, and there's a wall that separates the hot fluid from the cold fluid. Okay, so there is a wall that separates hot and cold fluid, and from the hot fluid, heat will be transferred to the wall, and through the wall, it will be conducted, and from the wall again, the heat will be convected to the cold fluid. So what is that? From hot fluid to the wall, so this is convection. Through the wall, it is conduction. And from the wall to the fluid, wall to the fluid, convection. Okay, so this is how the heat transfer takes place. Now, so you may be having doubts, right? Is it only conduction and convection is combined? What about radiation?
Every body radiates.
Yeah, of course, there is a radiation heat transfer also involved most of the times. Okay, and we have to make some simplifying assumptions by comparing the magnitude of convection and radiation. Okay, convection and radiation heat transfer to the wall. And many applications, we will find that radiation heat transfer is comparatively smaller to the convection heat transfer, and we can neglect. Okay, so that is, you can also understand that by remembering the Stephan-Boltzmann law, right? What we have there is the heat transfer, the Stephan-Boltzmann constant, sigma. So what is the value? I think I did I give there?
5.67.
5.67 into 10 power minus 8. So the constant is very small there. Okay, heat transfer. That Stephan-Boltzmann constant is very small. So you should have very large temperature difference between the wall and the fluid to have a appreciable quantity of heat transfer by radiation. Okay, so but we cannot rule out, okay, that component in some cases. Some cases it is there. Okay, that radiation heat transfer is also involved. So, but by making that assumption of the comparative study, comparative magnitude analysis, we can say that, okay, for particular cases, radiation heat transfer can be neglected, and we will consider only convection heat transfer from the fluid to the wall, and from the wall to the fluid on the other side. So heat exchangers are one example where we use this assumption. Okay, from the fluid to the wall, we will consider only convection heat transfer. We can neglect the radiation heat transfer there. So Okay, come into the one note is stuck. Okay, just okay. So at steady state, what we can write at steady state? Convection, Q convection, convection in on the left hand side equal to Q conduction through the wall, okay, and Q convection out. So since it is same, I will use the quantity Q only. Now to estimate convection heat transfer, which form, law we use? Convection heat transfer?
Newton's law.
Newton's law of cooling. So we can estimate Q convection, Q equal to Q convection in. So what is that quantity? We have given this very important value. Without this one, we cannot solve that problem. It will be given to you. Okay. So I think I have discussed there itself. The process of finding H value is not so simple. It's a research problem. Okay. Finding the heat transfer coefficient is a research problem. So you cannot just take this value. So we need some experiments to be done, and from the experimental results we have to derive the correlations, and from the correlations we can get this value of H. So right now for you it is very simple. The H value is be given to you, so you will use that without thinking much about it. So convection we estimate as H1, that is the heat transfer coefficient on the left hand side, okay, into area of heat transfer into the temperature difference, that is the temperature of the fluid Tf1 minus temperature of the wall T1. Okay. So similarly, you can write convection out, okay, and the conduction through the wall Q conduction. I think you already know this one, T1 minus T1 minus T2 divided by the thermal resistance, you can write, that is L divided by thermal conductivity of the wall into area. Okay, so here also you can write this one as Tf1 minus T1 divided by 1 divided by H1A. And further, I will write this as Tf1 minus T1 divided by RH1. RH1. This one I can write it as T1 minus T2 divided by RK. Okay, RK. So if you have multiple layers, then it will be depending on number of layers, you will get the conduction resistances K1, K2, K3, RK1, RK2, RK3. That will be same problem. Just now we have done composite wall. And then convection out. Convection out. That is, yeah, who is this? Any questions? No, right? Okay. So H2 is the Nachiketa, yeah.
since the wall and the fluid are in contact, shouldn't their temperatures be the same?
Which one? Okay. Let me write this first.
Like
I'll
TF1
complete.
and T1.
Sorry. T2 minus TF2. You are talking about TF1 and T1, right? Nachiketa.
Yes, sir.
Okay. So that means you don't have any heat transfer from the fluid to the wall. It will happen if you have a complete insulation to the heat transfer. Perfect insulation means there is no heat transfer through the wall, and you will have the wall temperature same as the fluid temperature. Understand?
But sir, for the wall, we assume that because the heat transfer is taking place, there is a temperature difference of T1 and T2.
Oh,
But for the
okay.
fluid, we are taking
Okay.
throughout the fluid.
Yeah. Okay, so Nachiketa, I got your problem. This one, I doubt. Okay, I understood. So, can you see this temperature profile here? I am highlighting the temperature profile there, right? Here, T1 is the surface temperature. And what do you see here? Is a continuity? Right.
Yes, sir.
The temperature increases, right? The fluid very close to the wall has the temperature of T1. You're right. Okay. The temperature of the fluid, which is very close to the wall, is very near to the T1, or slightly higher. And that temperature will increase in the temperature boundary layer or thermal boundary layer, we say. And when you go very away from the wall, you have the temperature of the fluid, TF1, which is called bulk temperature. Okay, bulk.
Okay.
Understand? Bulk fluid temperature. So that temperature is okay. That is considered in the estimation of heat transfer, not the exactly very close to the wall. Okay. Yeah. So H2A2 into T2 minus TF2 is the convection out, and we can write this one as T2 minus TF2 divided by 1 by H2A, and this is nothing but T2 minus TF2 divided by RH2, right? So same process now. We can write the this one. We can add the thermal resistances from the circuit. You can directly write what is the rate of heat transfer at steady state, or you can write and add those three equations that I will write. Okay, TF1 minus T1 is nothing but Q into RH1. Similarly, T1 minus T2 T1 minus T2 Q into RK, and T2 minus TF2 is Q into RH2. Okay, so you see the equation here. Add these three. What do you get? Is TF1 minus TF2, okay, equal to Q into sum of the resistances RH1, RK plus RH2. So Q is nothing but overall temperature difference, that is the fluid inside fluid temperature minus outside fluid temperature, divided by the resistances RH1 plus RK plus RH2. So now you can differentiate why I used the H1, H and K in representing the resistances. So K stands for conduction resistance, H stands for convection resistance. Okay. And you know how to write these resistances. So convection resistance RH1 is given by, so this we are writing first time, so I will write again 1 by H1A. Yeah.
Sir, this problem won't be a convection problem if the surface temperature of the wall and that of the liquid is maintained equal, right? Then it would simply be a convection.
Yeah, that's what I am telling you. If you have that condition that TF1 equal to T1 in the bulk of the fluid temperature and the wall temperature is same, that means there is no heat transfer from that wall. Okay.
From that wall.
Yes, there is no heat transfer at all, because if there is a heat transfer, then obviously the wall temperature will come down and the temperature gradients will be established. Okay, and you have the heat transfer. Got it right?
No, sir.
Okay. Yes. So we have the formula. So now everywhere you can see that formula takes, okay, finally you can write easily using this electrical circuit. That's all. Only thing is should know what is the convection resistance, what is the conduction resistance, and again what is the convection resistance. Okay, one more important quantity here is I'll substitute for Q. Q equal to TF1 minus TF2 divided by, tell me now what is RH1? 1 by H1A. RK, tell me what is RK? Thickness of the wall, that is L divided by K thermal conductivity into area, and then the second convection resistance, 1 divided by H2A. Okay, so if I want to write this one in the same form as Newton's law of cooling, okay, this is, for this one I use another symbol, not H but U. Okay, I'll instead of H I will use U now. Okay, so if I want to write that, then what should be my U value? Tell me. So I'll write this U as 1 by H1 L by K, then 1 by H2. Area is common everywhere, that can be taken out, and then we have TF1 minus TF2. Okay, so what is this U? The formula for U is now, yeah, who will tell me? Adit? Adit, are you there? So only 2-3 people will answer the questions. Abhiraj? Ali Adi?
Sir.
Yeah, tell me, what is the formula now? Look at this equation and tell me what is U. Look at here and tell me what is U. Ali Adi. U equal to why it's so difficult, man? We have area there, here also we have. Okay, TF1, here also we have that same. So that remaining should be U, right? What is remaining?
So 1 by 1.
1 by
1 by H1,
1 by H1
plus L by K.
L by K plus
1 by
1 by H2. So this is very important. Okay, this is called overall heat transfer coefficient. Okay, overall heat transfer coefficient. So it will take care of convection resistance, conduction resistance as well. So that's why it's called overall heat transfer coefficient. So Q can be estimated as overall heat transfer coefficient into area into TF1 minus TF2. Somewhere in the problem, if it is mentioned, overall heat transfer coefficient for the wall is this, and the fluid temperature is given. So you should not be worried. Okay, you should know it's a very easy problem to solve. Okay, because U is directly given, you don't have to worry about H1 value, K value, and H2 value. Simply substitute and obtain the heat transfer. Okay, so now we will move on to the next problem, that is composite, conjugate or combined heat transfer in cylindrical wall. So 1 minute. So the computer is stuck. Little problem here. Okay. Okay, so that's the problem here. Some issue with my laptop. Combined. So some issues with the OneNote jumping. You can see, right? Something is wrong here. Can you see the OneNote still?
Yes, sir.
Yes, sir.
But why is the multiple pages are appearing here?
Yes, it's glitching, sir.
Can you
Now
see
it's
now,
working.
Mitch? Okay. So consider the cylindrical wall now. Okay. So in cylindrical wall, we have to be more careful here in case of convection resistance. Why? What is the reason? Combine conduction and convection. See my handwriting. So it's issue. So why we need to be careful about this convection resistance? Because we have to consider the area. Area is different at inner side. The area is smaller, and outer side the area is more area outside. So you should be very careful here. Now, otherwise the problem is simple. So again, we have the three resistances: RH1, RK, and RH2. Okay. So tell me now we can write RH1 equal to 1 by H1 into area inside. Okay, or A1 you can write if you want, and RH2 is 1 by H2 A2. Conduction resistance for the cylindrical wall, who will tell me?
Sir,
Yes, Srinivas.
1 by K1 ln R2 by R1 into
No,
1 by
conduction resistance. This is cylindrical.
yeah.
Always start with ln.
ln R2 by R1.
Yeah, R2 by R1. ln R2 by R1 divided by
K
2
into 2
pi
pi L.
L K. Here we have only one wall, so K.
I was saying separately.
Yeah, tell me. Okay. Any doubt? So the steady state heat transfer is Q equal to, the process is same. Okay, you can write, okay, Q convection is equal to H1 AI delta T, that is TF1 minus T1, and similarly for conduction and again convection. So finally you will get TF1 minus TF2 divided by three resistances, that is RH1 plus RK plus RH2. So can I write now overall resistance here also, overall heat transfer coefficient? Substitute for the resistances. So you can write this as U A delta T form. Okay, you have to write in that form. So to do that, first I will substitute the resistances. TF1 minus TF2. The resistance, first one is 1 by H1 AI plus ln R2 divided by R1 divided by 2 pi Lk. Third resistance 1 by H2 A2 A outer A. Okay. Now write the areas first. You know, A inner area is at radius R1. So 2 pi L, 2 pi R1L, 2 pi R. R1 L, and A outer is nothing but 2 pi R2 L. So outer area is more than inner area. Okay.
So,
Yeah.
so L is the vertical length, right, of the wall?
Yeah.
That
Length of the. Okay, I think I have not shown these images, but first one I have shown, right? This is the length of the cylinder. Okay, L.
Okay, sir. Thank you.
So that will remain same. Okay, that's it. Okay.
So, here also Q convection in equal to Q conduction equal to Q convection out.
Yes, exactly. Okay. So now what is my problem is I cannot take out one area because you can see that this area is different, this area. Okay. So if I want to take out one area, then I have to, for example, if I want to take out AI, then I can write this as UI AI delta T. I'll write simply delta T is nothing but TF1 minus TF2. So now my UI is, what is my UI? Tell me, what is my UI? 1 divided by 1 by H1. Since I have taken AI outside, I should multiply here AI ln R2 by R1 divided by 2 pi Lk. And again here also I should multiply AI by AO into 1 by H2 into AI delta T. Delta T or okay, TF1 minus TF2. So this is now AI. UI. So instead of taking AI outside, I can write in terms of outside area, that is U0 A0 delta T, or TF minus F1 minus TF2. So what is the formula now? U is nothing but 1 by A outer divided by A inner into 1 by H1 plus A outer into ln R2 by R1. What happened to this one? 2 pi L K. Then 1 by H2 into A0 delta T. So the overall heat transfer coefficient in case of cylindrical wall, okay, we can define either based on inner wall area, inner side area, or outside area. So Q can be defined as UI AI delta T equal to U0 A0 delta T. This means we can write UI AI equal to U0 A0. This is very important relation. Okay. So overall coefficient multiplied by area is always constant for a cylindrical wall. Okay. So that you have to remember. Overall heat transfer. So those who students, I think, have taken the elective design of heat exchangers. This is used in your okay class. Yeah, overall heat transfer coefficient based on.
So the overall heat transfer with respect to inner wall is same as the heat transfer with respect to outer wall.
But the product not the same. Okay, product of area with this one, not some same. If you are not multiplying the area, then it's not same.
No, sir.
UI is not equal. Yeah.
I'm saying heat transfer.
Heat transfer rate is same through the wall. Okay. Inside area. and O is the coefficient based on outer area. Okay. So similarly, you can do it for the spherical wall. Okay, but we don't have much applications of that. But this is a very good, very much useful in the design of heat exchangers. Okay, so heat exchanger analysis, we use this. Okay, the final very important, yes.
Is the heat transfer problem in which the input is through convection and the desired output is through conduction?
What is that question? Can you repeat that question?
Yeah. So, sir, where the heat transfer input is through convection and the output is desirable through conduction. So,
in which application?
Yeah, is there an application? Is it practical?
Conduction, probably heat treatment, maybe. Kind of.
So, for instance, is this problem only if there is no H2, and let's say it is a composite.
Okay, yeah, that's all. That may be there. That application may be there. Some heat treatment of metal or something. There you want to heat the metal from low temperature to high temperature. So whatever heat transfer is into the material and is stored into that. So it's a kind of transient problem, not a steady problem again. Okay. Yeah. So we'll move on to the next very important topic, that is critical thickness of insulation.
So what about conduction and convection through spherical walls?
Yeah, you can do it, right? There is nothing extra here. Only thing is what I have shown you. To calculate the overall rate of heat transfer, you need to know the temperature difference of inner fluid and outer fluid divided by the resistance. Okay, so area only you have to take care. For the spherical wall, inner area is 4 pi r square, r1 square. Outer area is 4 pi r2 square. And the this conduction resistance, is nothing but r2 minus r1 divided by 4 pi k r1 r2. Nothing else. Okay, so process, everything is same. So but it's skipped because it doesn't have much applications again. Okay, so only that is the reason. So we are not going to use that overall heat transfer coefficient for that. Just you can estimate the rate of heat transfer. Now, very much practical example here I am taking is the critical thickness of insulation. So if you consider a electrical wire, okay, and after you allow the current to flow through that wire, you will come to know that its temperature will increase. Okay, temperature will increase. So T will be greater than, or surface temperature is greater than atmospheric temperature. So because the wire has some resistance, okay, if it is having zero resistance, then superconducting wire, then it's very good because that will give us no losses. But generally, if you take very high thermal conductivity material also, we have some resistance in the wire, and because of that, heat is generated and the temperature will increase. So there will be insulation around the wire. So one, it will provide the safety from the electrical accidents. Okay. The other thing is it also helps in increasing the rate of heat transfer. You are providing the insulation, and see my language is completely strange, maybe, right? I'm talking about a insulation which increases the heat transfer rather than decreasing. Okay. So what is this? How it is possible? For that we have to do this analysis. So consider that insulation is shown here, and say this temperature inside here is T1 and the outside temperature is T2. Okay, and there is fluid which is air, and the heat transfer coefficient is HA. The radius of the insulation at inside is Ri, and at the outer radius it is RO. Okay, outer radius RO. Here the surface temperature, because it's contact with the solid inside again wire, so surface temperature is same as the insulation temperature. We can assume that surface of the wire. Okay, so this is the wire and there is an insulation around it. So this is R1 and the outer radius here R2. This is the insulation. So here temperature is T1 and this temperature is T2, not A, T2, and then there is a fluid air and the convective transfer coefficient is. So when we want to find out the rate of heat transfer through the insulation, okay, we need to consider two resistances. One is the conduction resistance through the insulation, and other is the convection resistance on the outside surface. Okay, so rate of heat transfer we can write Q equal to temperature difference, that is T1 minus TA divided by resistance RK plus RH. Okay, or HA, air resistance. So any doubt here, or you don't understand anything? How can I write this? So we have the inside temperature known, T1, and there is a material, insulation material of thermal conductivity K. Okay, and then from the insulation outer surface there is a heat convection to the air. Okay, so we have two resistances. One is conduction resistance, another is convection resistance. So tell me what is conduction resistance, because this is a cylindrical case. So conduction resistance RK. What is RK?
ln
ln
R 2 by
outer,
R
inner. Okay, so for here I have used R outer and R inner. Okay, then divided by 2 pi L K. Okay, any doubt? No, right? Okay. So then what is the convection resistance outside? Come on. What is the resistance outside? Convection resistance. HA into outside area.
A.
Yeah. So tell me what is the H outside area? Area
2
is
pi
what?
R naught L.
2 pi R naught into L. 2 pi R naught into L. Now you observe closely and see the variation of H, RK and RH. RK increases with RO because ln R0 by Ri. Okay, if you increase R0, then RK increases. What about RH then?
decreases.
Yes. Because we have heat transfer coefficient is almost constant for the, okay. Then we can see that in the formula, Rho is coming in the denominator. So if you increase RHA, decreases. So this is the phenomena, okay, which makes that with the increase in thickness, okay, there is a decrease in resistance to the heat flow, depending on which decreases faster or which increases faster. Okay, so if Rk increases rapidly, then RH decreasing, then we will not get that. But Rk increases slowly compared to the decrease in RH. Okay, then with increase in Ro, we can get less resistance, and then we can have more heat transfer through the insulation. So it's, you have to think about it, okay, how the Rk and RH will change with Ro for a fixed Ri. Again, we have the condition here, Ri is fixed, okay. Cannot simply go on changing Ri also. Ri is fixed. So understand here, I think, okay, time is over, but we can think about this problem, okay, and ask if you have any doubts, questions. Okay. So basically,
So what had to,
ah,
yeah. So could you repeat the part that you had said about by increasing the insulation, we are actually increasing the heat transfer?
yes, yes. So depending on which quantity, okay, if our thermal conductivity increases more than RH decrease, what will happen? The total, right? If Rk increases more than RH decrease, then whether this total decrease?
Total decrease, yeah.
No, understand, Rk increases, RH decreases. But if Rk increases more than RH, then the total also increases. So there is no decrease in heat transfer. But
So
if Rk increases
if RK
slowly,
increases, then Q will decreases, right?
yes, exactly. So I'll tell you slowly. If Rk increases more than RH, decrease. Okay, then the total quantity also increases. So Q will decrease. But if Rk increase is less compared to RH decrease, then the total quantity will decrease. So Q will increase. Understand that? Okay.
Yes, sir. And sir, so how do we decide which one is faster?
Yes, that is depends on the constants K and H. Okay, so you can see that other things are all geometric things. Ri will be fixed, K and H will decide that. So we will find out that. Okay, so basically you can write Q equal to T1 minus TA divided by, what is this? We have the Rk, that is ln R0 by Ri into divided by, sorry, 2 pi Lk, and here we have 1 divided by 2 pi R0 L into HA. So the common things like 2 pi L, I can take it out and take it to the numerator, simply 2 pi L, and also with that I will take the thermal conductivity also into T1 minus TA. Then what is left here? I have taken 2 pi Lk to the numerator, so I have simply ln R0 by Ri. From this one I have taken 2 pi L and K also taken, so I should write K here, divided by H0 into R0 into H, R0 into HA. So numerator, we don't have any control because Once you select the material, K is fixed. Okay, length, all those things will be will not affect, but the denominator, that is the very important thing for us. That will decide the whether the heat transfer will increase or decrease. The quantity ln ln R0 by Ri plus K divided by HA into 1 by R0 will decide the rate of heat transfer. And clearly you can see that with R0, ln R0 by Ri will increase, whereas K by HA 1 by R0 will decrease. So if I make a graph, so my needs a resistance, okay, resistance, and this is R0. With respect to R0, I am plotting these quantities. So if you plot ln R0 by Ri, so what you get is the increasing graph. So this is ln R0 divided by Ri. Whereas, okay, K by HA, so where it will start? Tell me. This one, this quantity, okay, where it will start? Huh?
ln R0 Ri won't start from 0.
Okay, this is okay, right? It will start from, okay, here. Okay,
So it
for particular.
Start from Ri. On RO.
Yeah, okay, we have to start it from Ri. So there's no point in going below Ri. Okay. So anyway, then okay, this is a large quantity initially, yes, because small R0 means the large quantity, then it will decrease with okay. So this is nothing but ln H by HA into 1 by R0. Now you need sum of these two. Okay, that quantity, how you do that? How you sum these two? You have one value here. Okay, this is the RK value. And what is the R? So the quantity from year to year, etc. What is this quantity? What is this quantity?
The difference.
RH.
No, this is RK and this is RH. RH or K by HA into R0. That is okay, really. So if you sum these two, that means I have to add, what is this, RK here. Then I will get that point. So that means adding these two curves. I am adding the two curves to get the total.
So, but the intersection would be critical value, right?
Yes, not intersection is critical. You have to add these two quantities and find out where the minimum is there. That is the critical radius.
Should be right above the intersection, right?
How come? That is the misunderstanding.
Okay,
that is. I don't know where exactly it will come. It may come here also. It may come here also. Okay, then it will start increasing. That depends on the slope of these two, or the nature of these two. Okay, line curves. So only thing is you should know that this is a summation of the two. So that is a summation of two curves. difficult to trace. Okay, so how do you find the minimum of a curve? This one we know already, that is nothing but ln r0 by ri plus k divided by ha into 1 by r0. This is a function of r0, right? So now you know how to find the minimum of a function f of r0. Okay, how do you find the minimum?
Differential equal to 0.
Differentiate at minimum df by dr0 is 0. So differentiate this function with respect to r0 and equate it to 0 and solve for r0. You have the radius. Okay, that is the radius of critical radius of insulation. So find out that value and tell me in the next class. Okay, so you have the equation here. You differentiate this, you will get, can you tell me quickly what do you get? Ln, if you differentiate with respect to r0,
1 by r0 ri.
1 by r0, okay, then plus a by h. So here you have confusion why ri is not there. So you can write this one as ln. So if you want, I will write clearly for you, because there are some students maybe from poor mathematical background. So f of r0 can be written as ln r0 minus ln ri plus, any objections here? Law of indices, okay? Now you take the derivative df by dr0, that is 1 by r0 plus k by ha. What is the derivative of this one? 1 by r0. Already we have done it.
Minus 1 by
1 minus 1 by r0 square. Solve it and you have the r0 equal to
k by h.
What is that? K by ha. So your inner radius should be less than this one, r0. Otherwise, it's not possible to have a critical thickness of insulation. So ri should be less than rc. Okay. So this is nothing but rc, critical thickness of insulation. Critical radius of insulation. There is slightly, problem is when we talk about the critical thickness. What is thickness?
RO minus RI.
RO or RC minus. Thickness is nothing but RC minus RI. Okay, that should be mentioned. But critical radius of insulation means RC. Critical radius is RC equal to K by H. Okay. So that is right. Done. So today, then I will stop here today, and you can try for the spherical case. Okay, for the spherical case, you can try, and we'll discuss that in the next class. Okay, any doubts? You can ask me in the next class. Okay, so yes, so you have any doubts?
Sir, in case of sphere also, UO AO delta T equal to UI AI delta T, right?
Yes, exactly.
Overall heat transfer is same. Okay.
That is same. Yes.
Okay.
So it's proportional to area. Okay. Yes. Okay. Yeah, I'll stop here today. We'll continue on Monday.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay, welcome. Yeah.
So